It is a quiet morning in a materials laboratory, and an engineer lifts a block of metal the size of a brick. She expects the weight of a hammer. Instead, the block floats up in her hand like balsa wood. The metal is full of holes, and yet it is strong enough to stop a bullet. This is metal foam, and it may be the quiet revolution holding up the next generation of spacecraft. To understand metal foam, one must first abandon the idea that metal is solid. For most of human history, the strength of a structure came from mass. A thicker wall, a heavier beam, a denser hull. Metal foam appends that logic. It is a material whose strength comes not from what is there, but from the careful arrangement of what is not. The principle is borrowed from nature. Bird bones are hollow, laced with internal struts that brace them against the forces of flight. Bamboo grows in chambers separated by rigid walls. Coral builds vast reefs from porous calcium. Engineers studying these structures noticed a pattern. Strength does not require solidity. It requires geometry. The first patents for metallic foams appeared in the 1940s, the work of an American inventor named Benjamin Sosnick. He blew vapor through molten metal and watched bubbles freeze into place. The result was a strange new substance, light as wood, rigid as steel. For decades the idea languished, too expensive, too difficult, too far ahead of any need. It waited for an industry hungry enough to find it. That hunger came from above. By the late 20th century, the cost of sending a single kilogram into orbit had become a tyranny of its own. Every gram of structure was a gram stolen from payload, from fuel, from the mission itself. Engineers searched for materials that could do more with less. They wanted the impossible, a metal that weighed almost nothing. Metal foam answered the call. A typical aluminum foam contains between 70 and 90% empty space. It can be cut, welded, and machined like ordinary metal. Yet a panel of it weighs a fraction of its solid cousin. For a rocket designer, the implications are dizzying. A lighter spacecraft is a cheaper spacecraft, and a cheaper spacecraft can fly more often. There are two main families of metal foam, and they are made in very different ways. The first is called open-cell foam, a tangled network of metal struts with pores that connect like the chambers of a sponge. The second is closed-cell foam, in which each bubble is sealed inside a thin metal wall. Open cells breathe. Closed cells armor. Each has its place in the architecture of flight. To make a closed-cell foam, engineers mix a powdered metal with a foaming agent, often titanium hydride. They press the mixture into a billet and heat it past the melting point. The foaming agent releases gas, and the molten metal puffs up like bread in an oven. When it cools, the bubbles are locked in place forever. What emerges is a solid filled with a frozen storm. Open-cell foams demand a different art. A wax or polymer template is first shaped into the desired lattice. Molten metal is poured around it, and once the metal hardens, the template is burned away. What remains is a perfect negative, a skeleton of metal where the wax once stood. The result is a structure of astonishing precision, designed pore by pore. The properties of these foams astonish even the engineers who build them. A block of steel foam can absorb impacts that would shatter solid steel. The collapsing bubbles soak up energy in a controlled cascade. A bullet fired into a panel of composite metal foam slows, deforms, and stops, often without piercing through. The metal does not resist the blow, it swallows it. For spacecraft, this property is not a luxury but a necessity. Low Earth orbit is filling with debris. Flecks of paint, lost bolts, fragments of dead satellites, all travel at speeds approaching 8 kilometers per second. At such velocities, a paint chip strikes with the force of a rifle round. A spacecraft hull must survive an unending storm of microscopic bullets. Researchers at North Carolina State University, led by Afsane Rabiai, have spent years testing composite metal foams against this threat. Their experiments show that foam panels can stop high-velocity projectiles that pierce conventional aluminum like paper. The foam also blocks radiation, both the heat of re-entry and the cosmic rays that bombard astronauts in deep space. One material, 3 problems solved at once. Heat is the silent killer of spacecraft. A capsule returning from orbit must shed energies that can vaporize steel. Traditional heat shields are heavy and single-use. Metal foam, with its labyrinth of voids, traps heat in pockets of trapped gas. Tests suggest that foam panels can endure surface temperatures above 800 degrees Celsius, while the interior remains cool enough to touch. The European Space Agency has explored metal foams for landing gear and crash structures. The American military has tested them as armor. NASA has studied them as radiation shielding for missions to Mars, where astronauts must survive months beyond the protection of Earth's magnetic field. Each application begins with the same simple wonder. A metal that is mostly nothing performs better than a metal that is everything. Yet the road from laboratory to launch pad is long. Metal foam remains expensive to produce in large quantities. Quality control is difficult, since no two bubbles are quite alike. Inspectors must develop new techniques to peer inside the foam without breaking it. The promise is enormous, but the manufacturing is still a craft, somewhere between metallurgy and baking. Some of the most ambitious work is happening in additive manufacturing. Three-dimensional printers can now lay down lattices of titanium and aluminum with pore patterns designed by computer. Each strut is placed exactly where the stress demands it, and nowhere else. The foam is no longer random. It is engineered, atom by atom, for the specific forces it must bear. This is a profound shift in the philosophy of design. For centuries, engineers shaped solid blocks by cutting away what they did not need. The new generation builds only what the structure requires, leaving the empty space in place from the start. The result is a kind of architecture inspired by bone, light, strong, and grown rather than carved. It is a closer kinship between machine and living thing. If metal foams fulfill their promise, the spacecraft of the coming decades may look subtly different. Their hulls will be thinner yet tougher. Their heat shields will be reusable. Their interiors will shield astronauts from radiation without the bulk of lead or water. The savings in mass will ripple through every system, from the engines to the fuel tanks to the launch vehicles below. There is a poetry in this. The vehicles that carry humanity beyond the Earth may be built from a material that is mostly absence. The strength of the spacecraft will come from the gaps, the bubbles, the carefully arranged emptiness within its walls. Engineers are learning what nature has known for billions of years. Sometimes the most powerful structure is the one that knows what to leave out. Back in the laboratory, the engineer turns the foam block in her hand. Sunlight catches the cut face and she can see the tiny chambers inside, each one a sealed room of trapped air. It is metal, and it is mostly nothing. It is light enough to float on water, strong enough to stop a bullet, and patient enough to wait for the day it carries someone home from Mars. The next spacecraft, it turns out, may be held up by holes.